Hello, let's continue Equilibria. Looking today at indicators in acid-base titrations. For our objective, we're going to understand pH changes in acid-base titrations and how to select an appropriate indicator for certain reactions. So a titration is an experimental technique that we've looked at previously before. It is very useful for determining the concentration of an unknown solution. And how you do it is you have a setup something like this, where you have a piece of glassware called a burette, and then you have your conical flask, and the idea is that you're going to mix these two, the titrant, which is the species in the burette, you're going to mix it with the analyte, which is the species in the conical flask, and you're going to react them in the perfect stoichiometric ratio of the reaction, so that you're able to determine an unknown concentration from a known concentration, just using some straightforward stoichiometric calculations. So the titrant in the burette, that's the species that you have the known concentration. The analyte in the conical, that's the unknown concentration species. So yeah, the titrant, the known solution, is added from a burette. You add it small amounts at a time. So theoretically, like I said just before, you can react it in that perfect stoichiometric ratio. To a known quantity of the analyte, which is the unknown solution. Now the question is, how do you know once that reaction has taken place, once we've had that perfect ratio of our reactants and our products, of our reactants to make our products more accurately? Well, we can use these things called indicators. Now there's a number of different types of titrations in this Equilibria unit, and feeding on from what we were looking at in the last lesson with pH, we're very much looking at acid-base titrations. So we can use indicators that are able to, as their name suggests, indicate when a certain pH has been achieved. So an unknown solution will have an indicator, can use the change in pH and therefore the color to determine when the reaction is complete. So there's all sorts of varying levels of complexity. You can have electronic pH meters that you can put directly in your solution. It'll give you a number, but much more sort of straightforward than that is just using color change. So certain color changes will tell you when a pH threshold has been reached. What have we got here? The point of color change is the end point of the reaction. So when we've added the titrant to the analyte where we see a color change, we can call that the end point. Don't get this confused with what's called the equivalence point. We'll talk in depth a couple of times about the differences between these. Very similar sounding names, but two different things they're describing. So then once we've got the volume, and we have a volume and a concentration of our known, we have an unknown concentration, but a known volume of our analyte, of our unknown, we can use some good old stoichiometry to determine what our unknown concentration is. But look, we've looked at that before. We've got videos there if you are so inclined to revisit that. What we're looking at now are these indicators and how we can select appropriate indicators for appropriate acid-base titrations. So they give they give a sign, often color changes, of the presence or the absence of a threshold concentration of a chemical species. And we're often using pH indicators that tell you when the pH changes based on color changes. Fantastic. So let's have a look at some of these indicators. There's a whole variety of them, a bunch of different ones. I've just got a few, maybe more common ones, a few select ones showing their name. If I move that little bar out of the way, showing their name, showing the pH range that they operate within, where their endpoint, and then the color change that is observed corresponding to the type of indicator that we have. So what's there to say about these? An indicator is a dye or a mixture of dyes that gives a color change over a specific pH range. They usually have an endpoint where the color change occurs over a 1 to 2 pH range. So you can see the endpoints there for methyl violet is 0.8, but it can operate within this range from a pH of 0 to a pH 1.6, all the way down to the other end where we've got things like phenolphthalein and alizarin yellow. Hopefully I'm pronouncing that one right. Again, over that 1 to 2 pH range, 8.2 to 10, endpoint of 9.3. Now you might go, that's quite a large range considering we're on a scale that only goes up to 14. But as we'll see when we start to look at some of the graphs as we do the titrations and we observe how the pH changes, as long as you've got an appropriate one for when that ratio is reached, then you can still very accurately get your results that you need. So what's going on here? Generally, they're acting as a weak acid in equilibrium. Let's recall that Brønsted-Lowry definition of the acid as a proton donor. So again, generally, we have our indicator molecule, whatever it is. You can see there's a whole range of good stuff. And they've got a proton that's able to be donated where we can ionize the indicator, acting as a weak acid, implying that we've got that equilibrium reaction there. So we have one, which is a certain color. You can see some start red, some start yellow, others start colorless. And then once it's in the ionized form, we have a different color. And we can get the color change there, red to yellow, yellow to blue, yellow to an orange red, so on and so forth. Now, consider the position of equilibrium as the acid or alkali is added. So this is why it's very useful. We've said that we've got a titrant that we're adding. So, if this is an acid-base titration, we'll have an acid in there and a base in there, or, vice versa. We could have the base in there and the acid down there. And what's going to happen is it's going to change the position of our equilibrium here. We have our acids, which are proton donors. When we talk about protons, is that on? Yeah. Proton is essentially a H+. If you think about a hydrogen, the protium hydrogen at least, having one proton and one electron, if it loses that electron, it's essentially just a proton, isn't it? So if we add acid, we're adding proton donors. So essentially what we're doing is that we're increasing the concentration of H+. All that good stuff, Le Chatelier's principle predicts, if the system's at equilibrium, we disrupt that equilibrium, the system's going to shift the position of equilibrium to reestablish it. So, if we're adding acid, we're increasing the concentration of H+, so our equilibrium is going to shift to the left-hand side, and that's going to give us a certain color. If we're adding the alkali, we describe the Brønsted-Lowry definition of alkali as proton acceptors. If you got H plus OH minus, if you can imagine that reacting, and we're forming H2O, well, if you're adding alkali / base, I'm using them a little bit interchangeably. All alkali are bases, all bases aren't necessarily alkali. But look, for our purposes, if we're adding OH minus, we can think of that as a proton acceptor. Then what are we going to be doing? We're going to be decreasing the concentration of that hydrogen ion and pushing that equilibrium to the right-hand side. And again, we're going to see a color change accordingly as we change this pH, depending on what our species are and depending on the color changes they have. Titration curves. So let's get into the good part. So we're trying to find what's called the equivalence point. Remember, that's different to the end point. But that equivalence point is that, that theoretical idea of we've reacted our reactants in a perfect molar ratio, depending on what the stoichiometry of the equation is. It's not necessarily going to be the same volume. If we've got a stoichiometry that has different volumes reacting, it's just when we've got that perfect molar equivalent. So the point at which chemically equivalent quantities of reactants have been mixed. So in terms of our acid-base titrations, it's when we got the number of moles of acid can neutralize completely the number of moles of base, and we have the equivalence point. So that's the definition of the equivalence point, different from the endpoint. The endpoint is the point at which the indicator changes color. So we had all our endpoints up there. Now the endpoint's used to determine the equivalence point practically, but they're describing different phenomena. So just be aware of that. Equivalence point will depend on our acid-base combination. So we're going to look at a few different combinations. We're going to look at strong acids and strong bases. The equivalence points there will occur at a pH of 7 to form a neutral solution. But we could also have a strong acid and a weak base, in which case we're going to end up with a pH of less than 7. If we've got a strong acid and a weak base, we're going to end up in that acidic region, forming an acidic solution. And our third combination is the weak acid and the strong base, where the strong base means we'll form a basic solution at the end with a pH greater than 7. We'll go into all of those in depth one by one. But what we can do is we can plot the pH of the analyte against the volume of titrant added to obtain what's called a titration curve. So as we add our titrant little by little, we can measure the pH and then plot it corresponding to how much of that titrant we've added. And our shape of our curve, that's going to be dependent on our acid-base strength, the ones we decided up here. And it's also going to be dependent on if you're adding your acid to the base or your base to the acid. All the graphs I've got here are all looking at adding an acid to the base. but that's saying the acid's in the burette and we're adding it to the conical, or the Erlenmeyer, if you will. But there's no reason why we couldn't do the other. If we got the base as the known concentration and we're adding that to the acid, the same ideas, the curve will be it'll be sort of inverted. We'll go through some examples though. What you might notice though is that there's a combination of acid-base strength that is very much missing on my 3 dot points there, which is the weak acid and the weak base. These combos tend not to be done because there's no sharp fall with a gradual color change of indicator. It's insufficient for the accuracy required from titration. What does that mean? What are we talking about with these, with the sharp fall? Well, it looks something like this. So let's go through our first example. We've got the strong acid and we're adding that to the strong base. So if I draw a real crude little titration setup, something like that. Not the best picture, but that'll do. So, we've got the strong acid and we're adding a strong base. So I might get blue, blue's a bit easier to see. So we're starting with the base. So we're measuring the pH. So we're up in that basic region. It's strong, so we're very basic. And then as we add the acid little by little, it's going to slowly move. Well, not necessarily slowly move, but it's going to move into the acidic region. It's going to move to that lower pH, which is what we observe in the long run, but there's a pretty quirky trend going on there. So let's have a talk about what's happening. pH drops a small amount until we near that equivalence point. So let's have a look. So as I'm adding my acid to my base, we have volume of titrant added. As I'm adding more and more, little by little, I'm measuring the pH. We have a small pH drop, but once we reach this equivalence point, we can definitely see there's a huge drop off there. Then a steep fall. The midpoint of the steep fall is where the hydrogen ions have exactly reacted with our hydroxide ions. So we said before that a strong acid and a strong base, our equivalence point is going to occur with a pH of 7. So let's have a look where that lines up to on our graph here. pH of 7 neutral. So that is the equivalence point where we've had the acid and base completely reacted with each other. The H plus ions have exactly reacted with the OH minus. So the equivalence point is in there. So we notice at this point, the small changes in volume correspond with rapid pH changes around this region. So, if you go here, you're adding less than a mil. If you think about going from there, less than a mil later, you're all the way down there. So we've got these huge changes in pH around the equivalence point. So let's talk about how we can identify the equivalence point using the indicator, using what we talked about before, the endpoint, the point at which we get that color change. Because we've got a whole bunch of different indicators and we have a bunch of different acid-base combinations that we can have. So we need to pick an appropriate indicator for an appropriate acid-base titration. So we need to pick an indicator that has a color change over the steepest part of the, oh my goodness, all sorts of spelling errors here today, of the slope corresponding to the sharpest pH change. This large pH range accounts for minute changes in volume of titrant added. So this is why it's fine if our pH is, is changing, our indicator is changing color over a bit of a range of pHs there, because if you look at here, if you've got this massive drop, if I get some pink back, well, that's still blue, but my point still stands. This is occurring with a smallest amount of volume added, but we're talking a pH range goes from, a bit below 12 to a bit above 1. So that's a massive change in pH for a very small amount of volume. So what we need our indicator to be able to change color within this region here. So for example, we could pick a bromothymol blue or a phenolphthalein. There might be others as well, of course, but they're just ones off of my list I got here. Where'd my list go? All the way up here. So bromothymol blue and a phenolphthalein, because we look at these pH ranges, they are within that big drop that we have where the equivalence point lies. And we have an endpoint near where our equivalence point is going to be for our strong acid, strong base reaction. So let's have a look at both of those if I get all this up. Bromothymol blue. we have a pH range of 6.0 to 7.6, let's say around there. So you can see that as we're adding our titrant, as we're adding our acid to our base, once we reach this region, it's going to be a very small amount, but we're going to have that color change occurring right where our equivalence point is. So that can tell us that the reaction has reached that endpoint. Similarly, phenolphthalein, 8.2 to 10, similar sort of thing. Up here, 8.2 to 10. But if you look at how steep that curve is, you know, there's no real difference between the bromomethyl blue or the phenolphthalein. So they're both appropriate in this instance as indicators for this type of titration, as the color change corresponds to the sharpest pH region. All right, very quickly, what would this look like if we weren't adding the strong acid to the strong base, but instead the strong base to the strong acid, if the strong base was our titrant? That's a good question if you wanted to have a little bit of a practice. Sketch a, what are they called, titration curve for a strong base being added to a strong acid. Well, it'll look something like this. We've got our pH up on the y-axis there, and then we've got the volume of the titrant that we're adding. So our pH is going all the way up from 14, and then our volume of titrant, you know, for whatever the reaction is. Let's not worry about labeling that, but you know, that's going to be, let's say, milliliters. Cool. So let's consider what's going on here. We're going to have, if I draw a little titration setup, that's a curvy one, like that, like that, like that, like that. And then I might just freehand a little flask down the bottom there. So let's consider where we said that we're adding, what are we doing? We're adding a base to an acid. So we've got the base as the titrant, we've got the acid as the analyte. The acid is the unknown concentration. Well, if we measure the pH, we're going to be very much down here in this acidic region, aren't we? So, you know, let's consider as we add the base, we just said, similarly up here, pH drops a small amount. In this case, the pH would rise because we're adding the acid. Adds a small amount until, oh, I didn't know you could do that, until you reach the equivalence point, you know, for whatever volume that is for this particular titration. And then we see that really large, that sharp increase. Steep fall in our previous instance, it's going to be a steep rise in this instance because we're adding acid and then it's going to tail off. Sorry, we're adding base. It's going to tail off up in that alkali region because we're adding a strong base and a strong acid. So hopefully that makes sense. You know, we started off in the strongly acidic region down here and we're ending up in the strongly basic region up there. And then a strong acid, strong base combo, we would still expect that to have a equivalence point around 7 there. Fantastic. Let's keep looking at some other combos. What about if we have a strong acid and a weak base? Well, I'm going to describe it and then I'm going to ask you to draw it. How's that? So the analyte, what we've got in our conical down the bottom, or we're analyzing the analyte, the unknown, that starts weakly basic. And then we're going to have a sharp fall from pH 7.3 to 3.5. So again, we're starting with the weak base, we're adding the strong acid. So we expect it to go from the basic region into the acidic region. I'll tell you the equivalence point occurs approximately at a pH of 5. And the analyte finishes strongly acidic as we add this strong acid there. So yeah, like I said, here's a couple of questions. These will be good ones. So get me ugly mug out the way. Predict the shape of this titration curve by sketching the graph on an appropriate axis. You know, not dissimilar to what I did over here. It's not going to look like this one because this was our strong acid and strong base. However, I've described it with me words up here. And then explain why methyl red, which I've given you a pH range and an endpoint, why would this be a good indicator for that reaction? Give it a pause. Hopefully it looks something like this. So let's have a talk about it. We have the analyte starting off weakly basic. So look, we're up here. We're not right up in this pH of 14 that we had up for a strong base. It's weaker, so it's going to be a little bit below that. Still has to be above 7 because it's still got to be basic. But yeah, we're starting there, and then you add it and we still get that small decrease until we start to reach that equivalence point, and then that's where that sharp drop is with our equivalence point of 5. So the middle of that, we would expect that to be having our equivalence point there. And then it tails off and our analyte finishes strongly acidic. And hopefully that makes sense as well, because we're finishing with a strong acid. We're adding with a strong acid. So the more acid we add to that solution, the more lower that pH is going to become. Same way that we're starting with a weak basic, so we're not quite up at 14. We're much closer down there. So this combo means that we're going to end up with a mildly acidic equivalence point when our solution is at equivalence point, is what I'm trying to say there. So yeah, hopefully that makes sense with the different acid-base strength. Means the stronger acid means we have a mildly acidic equivalence point there. So why would methyl red be good? Well, we got the color change occurring within the region that corresponds with that sharpest pH change. So, let's take a ridiculous example here. Let's say we were using something like phenolphthalein, 8.2 to 10.0. Yeah, so let's say if we were popping phenolphthalein in there, 8.2 to 10.0, this is where it's changing color. So that wouldn't be useful for this particular acid-base titration, because the color change is occurring before our equivalence point. And at the equivalence point, we're already changed the color. So how would that detect the equivalence point? So yeah, that's what I'm trying to stress, is the fact that the equivalence point, our indicator needs to have the color change within this really sharp drop. So let's talk about methyl red then. Methyl red was a pH of 4.2 and 6.3. So look at that. That's the color change within that real sharp drop, where those very small amounts of titrant that we're adding are going to have huge drops in pH. Fantastic. All right, what about the weak acid and the strong base? So again, I'm popping what am I doing? I'm popping the acid in the burette. The acid is the titrant, and we've got the base in the conical. Again, it could do the other way, in which case these graphs will look inverted, like I've done over here, but we're just keeping it nice and consistent here. So our analyte starts strongly basic, because we have a strong base, and we have a sharp fall from pH 11 to 7.5. Trying to change it to the freehand, there we go. Our equivalence point this time is occurring at a pH of 9. So in that basic region, which is different to when we have the strong acid. Our analyte finishes weakly acidic. So here you go. This is what this one's going to look like. We have the strong base that we're starting with. So we're up in this region of 14 again, very basic. And then we have small amounts of titrant, depending on what our acid-base reaction is, will depend how much you've got to add to reach that equivalence point. But then we have the sharp fall from pH 11, which is there, down to 7.5, like that. And then, because we've only got a weak acid, it tails off like that as we add more and more weak acid, but we're adding a weak acid. So, there's only, I was trying to get the straight line. It can only get so acidic because it's a weak acid. So we end up with a mildly acidic solution there. Whereas with the strong acid and the weak base, we had a strongly acidic. Cool, and then we've got our equivalence point at a pH of 9. Look at that, halfway down that sharp drop. So the same thing, we can select some indicators for this titration. I've given you 3. In a test or exam, you might be getting a whole bunch of them. It's the same thing, and certain indicators can be used. There might be more than one appropriate indicator for sure. You can see a lot of these regions overlap. But again, you're just trying to find that equivalence point within the pH range that it's changing color. So if I were to give you only 3 from that list, what have I given you? I've given you a alizarin yellow, a methyl orange, and a phenolphthalein. And I've given you the appropriate data to use here. Which one of these would be the best? Operative word being best there for this particular titration. Give it a pause and let's compare our answers. I said a phenolphthalein is the best from the list as it changes color in the pH region corresponding to the sharpest pH change. All right, so let's have a look at why the other ones don't work. Let's have a look at the alizarin yellow, 10.1 to 13, 10.1 to 13. Well, you can see that's going to start changing color. That's going to start changing color back there where we're not at our equivalence point yet. So that's not going to be particularly useful. Our methyl orange, 3.2 to 4.4. Well, we might not even get to that color change. Well, yeah, maybe right at the end as we've added a lot of acid. But that's well after. You know, we're going to get the color change after the equivalence point. So again, that's not useful. So phenolphthalein between 8.2 and 10.0, 8.2, 10.0, look at that. We're right within that sharp drop, which is what we need from the indicator. Fantastic. Phenolphthalein is the best from the list as it corresponds in the pH region corresponding to the sharpest pH change. Fantastic. And then just to reiterate from earlier, you don't really do it with a weak acid and a weak base. I don't have a graph here, but you can pop on Google if you want to give it a little look. And what you don't have is you don't have these nice sharp drops there. And you know, the whole point of titrations is to be accurate. So let's just reiterate what I set up here. No sharp fall. So you get this sort of messy, elongated graph that's not particularly useful, insufficient for the accuracy required from a titration. So these are the only combinations of acid bases that we can analyze this way. Brilliant. As I scroll through everything, I think that brings us to the end. What have we done? We sketched the pH titration curves of titrations using combinations of strong and weak acids with strong and weak alkalis / bases. Selected suitable indicators for acid-alkali titrations. Given appropriate data, pKa values will not be used. And then, oh look, we did that last time, calculating the concentration of pH. That is more in that previous video. But for this one, here are the tasks. Give it a pause, give it a consolidate if you like. And that finishes it. Good one. Still a little bit more to go with Equilibria. So I look forward to the next one when we carry on. Fantastic. Have a good one. See you later.